Hello everyone, I am Sahil Surehali from Arizona State University. I am a graduate student working with Professor Rainer Nethalat. I'm going to talk about anisotropy effects in 3D printed concrete. So 3D printed concrete, as we all know here, is a form of additive manufacturing technology, and according to International Organization of Standard, there are 7 different types of additive manufacturing technologies, out of which material extrusion is the one that is most commonly used in 3D printed concrete. The usual process in extrusion-based 3D concrete printing is we generate a G code, which is fed into a 3D printer, and then material is put into the hopper, and through the pump, the material is pumped through a nozzle, and according to the G code coordinates, we get a 3D printed object. So the advantages of 3D concrete printing is we don't use foam work, so which reduces the cost of the overall structure drastically. The material is placed at places where it is structurally or functionally needed, thereby reducing the material usage. The material wastage is also reduced because now we are placing it through a digitally controlled nozzle. So we have a drastic reduction in cost, and there is an increase in productivity also. So those are the few of the advantages that this technology offers. Some of the recent applications of this technology across different parts of the world are a 3D printed bridge in Spain, and there's some habitats or housings that have been built in Italy and Netherlands. But with this technology, with extrusion-based 3D printing especially, we introduce interfaces in the in this object. So 2 different types of interfaces are introduced. One between the layers that is placed adjacent to each other, which is the interfilament interface, and another interface which occurs between the layers which are placed on top of the layer, which is known as interlayer interface. So both this interfilament and interlayer interface will introduce an inherent anisotropy in the 3D printed objects, and the number of interfaces, the quality of interfaces are all dictated by the printing parameters such as the layer height, layer width, and print velocity. So not surprisingly, as we change the print parameters, the quality of interfaces will change, the number of interfaces will change. So they will have an impact on the mechanical as well as the transport properties. Also, the interfacial zone will act similar to cracks, and they will offer minimal resistance to the transport of ions or moisture in the 3D printed concrete. Therefore, the durability properties must be investigated. So based on this background, the research objective for this study was to investigate the impact of layer heights and test directions and also fiber reinforcement on the compressive strength and transport characteristics of 3D printed concrete. We chose 3 different layer heights, 6, 13, and 20 mm, which were intentionally chosen to keep it smaller than the nozzle diameter that we used in our study, so that we have some pressure induced by the nozzle for extruding the layers. And the test directions, we tested all the samples in 3 different directions: along the direction of printing, along the direction of layer buildup, and the direction perpendicular to both of these. So we used a L30 mix in our study, which has been used as a standard printable mix in our group. This mix has 30% of cement replaced by limestone and comprises 50% of sand by total mass of solid in the mortars. We used basalt fiber and steel fibers as fiber reinforcements, and polycarboxylate ether-based superplasticizer was used. SP ratio in all these mixes were kept similar, and the steel fiber and basalt fiber ratio was 0.28 by the volume of the mix. So this is the 3D printer that we used for this particular project. It's a gantry-based printer. It has a controller from which all the printing parameters are controlled, a mixer which inputs the material into the hopper, and then we have the printing bed, and it's almost a 2 by 2 meter in 2 by 2 meter capacity in the plane systems, a plane of the printing bed. For compressive strength specimen, now we printed slabs with 3 different layer height, as I already told, 6, 13, and 20 mm. The layer width was kept constant as 20 mm, which is the nozzle diameter, and we extracted 60 mm cubes from each of the slabs, so which made sure that we had multiple interfaces, both interlayer and interfilament in all the tested samples. So if you see the figure on the right, it's from one of the 20 mm printed slab, and it shows the 3 different directions that we tested and for the compression strength. So when we test in D1 direction, the application of the load is parallel to the interlayer and interfilament interface. And when we test it in the D2 direction, the load is parallel to the interlayer interface. In D3 direction, it is parallel to the interlayer interfaces. So when we will extract samples from 6 and 13 mm layer height used slabs, we will have different number of interlayers, because now we'll have 10 layers for 6 mm printed slab for a 60 mm cube. We'll have approximately 4 layers for a 13 mm printed slab, and as shown, we have 3 layers for the 20 mm slab. So we have different number of interlayers that will come due to the difference in the layer height that is used. So based on layer height and different direction, we tested for both plain and fiber reinforced samples. So if we see for the results, compressive strength results for the plain samples in 6, 13, and 20 mm, we see that in 6 mm, all the 3 test directions, which is D1, D2, D3, have similar strength. And if we go to 13 mm and 20 mm, we start seeing anisotropy. So for this, if we see D3 direction, in all the 3 layer heights, it has similar strength. So D3 is the direction when the stress is applied parallel to the interlayers. And in compression, the interface which is parallel to the stress application direction is more critical to failure, as it is easier to separate. So because we used layer height smaller or equal to the nozzle diameter, we expect all the interlayers to have some transverse pressure, some pressure applied on during the layering, due to which the interlayer interfaces do not degrade that much as we increase the strength, as we increase the layer height, sorry. So due to which in D3 direction, we get similar strength. But when we go to D2 direction, which is the direction in which stress is applied parallel to interfilament interfaces, due to circular nozzle, we start seeing a rounding of the extruded layer, due to which defects are formed at the interfilament when we start increasing the layer height from 6 to 13 and to 20 mm, due to which we start seeing a drop in strength in 13 and 20 mm samples as compared to the 6 mm sample. For D1 sample, we'll have both interlayer and interfilament interfaces parallel to the stress application direction. But in 6 and 13 mm, we have more interlayers as compared to interfaces. So, and which is the stronger of the 2 interface. Sorry. So in 6 and 13 mm samples, we do not see a strength decrease, but as we go to 20 mm layer height, there is a strength decrease in D1 sample also. And this trend with direction of the strength dependence with direction remains similar for basalt fiber and steel fiber reinforced samples. But when compared to the cast samples, the fiber reinforced samples had a lower reduction in compressive strength. To put based on the compressive strength in 3 direction and the strength of the cast sample as compared to their for each mix, and we see that as the layer height increases, the anisotropic coefficient increases, and with the introduction of basalt fiber and steel fiber, we get a reduction in anisotropic coefficient, which is attributed to the load carrying capacity of the steel fibers, which compensate for the interfacial defects. So what we can learn from this is we can use lower layer heights of 6 mm if we want a near isotropic condition in compressive strength, and also use steel fiber to compensate for the interfacial defects. But if we already know the stress application direction and we have an idea of the principal direction, we can also use higher layer height by properly orienting the specimen in the direction where the principal stresses will be applied. Now, after doing the strength characterization, we wanted to characterize the durability properties also, for which we use a non-steady state migration test. And in this test, the samples are extracted from the slabs with, again, 6, 13, and 20 mm layer height printed sample. This is a representative sample extraction process from a 20 mm sample slab. We coat cylinders in 3 directions again, D1, D2, D3, and again, if you see the figure on the right side, based on the test direction and based on layer height, the number of interfaces and the quality of interfaces which is parallel to the transport direction, which is shown by differ. So when we tested these samples with NSSM test and characterized the durability based on diffusion coefficient, we had an interesting observation in D1 direction. If you see all the samples in D1 direction with different layer height, the chloride transport is on the bulk surface is used to calculate the diffusion coefficient on as D1A, but if you see the ovals, which is also showing the chloride transport, that is used to define the diffusion coefficient D1B. So why there is a increased diffusion in this direction? This is because in D1 direction we had interlayer and interfilament interfaces both parallel to the transport directions. So at the intersection of the interlayer and interfilament interfaces, there's a void formed which now becomes as the major path of transport for the ionic species. So what we concluded from this is, like, for 3D printed samples, in D1 direction we cannot actually rely on the diffusion coefficient for their durability properties, because if you see 13 and completely transported through the specimens, and it happened even before the test duration could be completed. Therefore, only D1B is defined for direction 1, and only for 6 mm it is represented. And even if you see the difference between D1A and D1B, it's about 1.5 times higher. So we concluded that the voids which are formed at the interfilament and interlayer interface will now become as the major transport path for the ionic species. This is not the case in D2 and D3 direction, because now we have only one interface which is parallel to the transport direction. So in D2 direction, which is the direction of layer buildup, the transport of chloride ions reduces as the layer height increases. This is because the interfaces which the ions have to counter are now spaced more at a more distance from each other, which is because of the increase in layer height. But in D3 direction, the interfaces which is perpendicular to the ion transport remains unchanged, because the layer width was similar for all the samples. So we conclude from this that interfilament interfaces are more dangerous for the transport ions, and if we need to reduce the interfilament interfaces in the printed samples, so we can use a larger width of the layer to reduce the interfilament interfaces. Similar observations were observed for the basalt fiber samples. Steel fiber samples were not tested for diffusion properties because of their conductivity in the specimen. To elucidate the porosity, we used MIP to do of the filaments, and as we see on in the table on the right, the porosity increased with the increase in layer height, which is because as we increase the layer height, the pressure applied by the nozzle starts reducing. So there is an increased porosity in the bulk region itself. And the critical pore diameter also increases, due to which the durability properties will be decreased. And then we defined a retention factor based on the volume of mercury intruded and extruded. And we see that the retention factor also decreases for the increase in layer height, which shows that in the bulk region, less mercury is retained, so the pore structure is now less tortuous as compared to the cast specimens. To find out the effect on the interfaces, we did X-ray computed tomography, and these are the specs for the XRT machine that was used for this. If we look at the figures from XRT just for the L30 mixture and different layer heights, 6, 13, and 20 mm, we clearly see that 20 mm has higher number of pores, and even the pore volume is increased as we see on the scales. And concentrated pores in a region, which are due to the which are formed at the intersection of the interfilament and interlayer interface, as shown in this slide. If you see this void, this is for a 20 mm sample. It is the void that forms the continuous channel through the specimen, and which was responsible for the enhanced transport of ionic species in the NSSM test also. And this is from a 20 mm sample, and similar was observed for 13 mm also, but in 6 mm, because of the more pressure, the voids were not as significant. Now, we used electrical impedance spectroscopy also, and we wanted to see the transport properties based on electrical impedance. And this is a circuit model that is proposed for conventional concrete, where different constant phase elements and resistors are used to depict different properties of the microstructure of the concrete, out of which the resistance of the unconnected pores of the connected pores is the most important for the transport properties. So we wanted to see how this model will work for the 3D printed samples also. So we did EIS for the L30 mixtures for different layer heights and different directions. And again, we saw that 6 mm sample has almost isotropic results, whereas in 13 and 20 mm samples, we see anisotropic results. In 13 mm sample, we see D2 has a higher resistance as compared to direction 1 and direction 3, which is mostly because in D2 direction, the number of interlayers start occurring at a larger distance as the layer height is increased. So the parameter extracted from EIS was related to the bulk resistance, and we found that good correlation can be established between the connected pores and the bulk resistance that is obtained for the samples. So the model that is proposed for the conventional concrete can be efficiently used for 3D printed samples also, and we can get a quicker measurement of microstructure properties from EIS for 3D printed samples also. To summarize, we found that presence of interfacial defects reduce the compressive strengths, but if we can properly orient these interfaces and use them as per our application, we can also use anisotropy to our advantage. And introduction of steel fiber, especially at the lower layer heights, can give us near isotropic conditions. The non-steady state migration coefficients were also dependent on the layer height and direction of testing, so we need to be careful while evaluating the durability properties of the 3D printed samples. And the X-ray computed tomography and electrical circuit models can be used to get microstructural parameters which can be related to the properties, the mechanical and transport properties. These are the references that were used for the slides. And finally, I want to acknowledge the US National Science Foundation for funding this study, and Salt River Materials Group, OMIA Basalt Fiber and Rock Fiber for the material donation, and 3D printing and material characterization facilities at Science of Sustainable Infrastructure Materials at ASU. Thank you.